you can explain that pretty nicely if this planet is orbiting a co-rotating and therefore very fast rotating host star. And that makes the host star gravitationally darkened, so it's darker at the equators than at the poles. And it also exerts a torque on the planet's orbit, which means that the orbital plane can precess. And it actually does that on a timescale of about 100 days or so, which matches, or of order 100 days, which matches that timescale of the changes we saw pretty nicely. You go to the next slide. So the point of my poster, which is outside, Jason Barnes was able to fit all this data and model it and make predictions of how the transit depth would change with time, and the transit shapes, in fact. So this is 2009 through 2015, a fit to our data and predictions of how it would go. And we've got data from Keck, Spitzer, and more recently from the LCOGT 1-meter telescope network. This all sort of fits on there, and it turns out it all fits pretty nicely so far. Right now I'm working on reducing some recent LCOGT data. We've seen the transits seem to have disappeared and then actually come back again, just as they should have done. They actually disappear for a couple of weeks a year, or a couple of months a year, and it all fits. And I will stop right there. Thank you.
Morning. My name is Julien Milly. I'm working with David Mouillet and Dimitri Mauer here at ESO. My area of interest is direct imaging of debris disks. So I guess you're familiar with this one, which was one of the target in the press release of both GPI and Sphere. Here we got last year images with NACO at the VLT in polarization. So polarization is very efficient to characterize debris disk because the light of the star is mainly unpolarized, whereas when it gets scattered by the dust grains, it requires a linear polarization. So here on the left, you can see this polarized image with NACO, and you see a very bright asymmetry between the northwest side and the southeast side. So one of them is much more intense, and this asymmetry is not seen in unpolarized light. So in the middle, you have an archival data from NICMOS, which we revisited for the purpose of this analysis. So this is very interesting because the current understanding of the scattering by dust grain in the framework of the Me theory, for instance, cannot explain this asymmetry if we believe that properties of the grains are like what the modeling of the spectral energy distribution suggests. Next slide, please. So another very efficient way to characterize debris disk is angular differential imaging. And here I would like to show you the recent result obtained on beta peak, an edge-on disk, so very, very good for ADI. We had to combine here these images at L prime, so we had to combine 7 deep data sets obtained at different epochs. And the interesting thing, is that we had to subtract the signal from the companion in order to reveal the disk in the more close-in regions within from 0.5 arc seconds to 1 arc seconds. Thank you.
I'm Jared Mills from the University of Arizona, and I just wanted to tell you real quick about some of our Magellan AO or MAG-AO results. Travis already apologized to me for skipping MAG-AO in his list of imaging systems. Everybody forgets about us. So over here on the right is an M-band image of Beta Pictoris b, very uncontroversial detection of the planet. No one would argue with us. I would highlight that that's at 3 lambda over d, and you can see the telltale signs of PSF subtraction, which I guess we're going to hear a lot more about this week. Over there on the left is the same planet, an image taken at the exact same time, and you see that little white bright spot there at exactly the correct location. And that's on a CCD. So with MAG-AO, we're pushing high contrast imaging and exoplanet detection down into optical and now visible wavelengths. If you go to the next slide. So that's a close-up of that planet. And so we're getting down to 10 to the minus 5 contrast inside half an arc second. And I have a poster up with some more details about this, and you can sort of see the hard work we did to make sure that this was real and see how we're doing. And also Kate Follett and Yalin Wu have posters up with Viz-AO results. And we also have stickers, so you should come talk to us for your free MAG-AO sticker.
Hi, I'm Mark Booth. I'm a postdoc working at the Pontificia Universidad Católica de Chile. And so my poster is on H8799. There's the picture that you will recognize with the planets at the top there. But I'm more interested in the debris disk, and so I've been looking at data from the far infrared to sub-millimetre. So we had a paper out earlier this year led by Brenda Matthews on the Herschel data. So what I think is one of the most interesting things to come from this paper is that when you look at the spectral energy distribution, that can be easily fit by just sort of two-temperature model. But clearly when you look at the images, there's dust going all the way out to 2000 AU. And so this suggests a wide planetesimal belt of sort of 200 AU and then a halo of blowout grains. Next slide. And now I've been working on the ALMA cycle 0 data of this. With the ALMA data, what you get is not the image. It's an interferometer, so you get the visibilities. This can then be translated into an image. Unfortunately, in this case, there isn't much to see in the image. But if you look at the visibilities themselves, you can still gain some constraints from those. So on the left, that plot shows the real component of visibilities, which can be used to get the inner edge of the debris disk and how wide it is, which actually implies that the disk must be wider than we thought from the Herschel results. And then on the right, you have the imaginary component of the visibilities. This looks to be essentially flat from the data, suggesting that the disk must be very smooth, and so there's no clumpiness seen in this image, as had been seen in some previous images of the system.
I'm Ewan Douglas. I'm going to talk about the picture sounding rocket. So we're looking at epsilon Eridani in the visible light. There's a bright IR excess at 24 microns that implies that there's a warm belt at 3 AU. And we're going to use a visible knowing coronagraph to look for that in 600 to 750 nanometers. So our knowing coronagraph takes a single pupil and shears it, so and then offsets one arm by pi, and we get an interference pattern as if we had two telescopes, but we're using a single telescope where epsilon Eridani is very close, and it's a very bright target, so we can get it in our 230-second observation window. We have to use a deformable mirror and a PZT to match those two arms, so we'll be testing MEMS deformable mirror in flight. Can you go to the next slide? So on the left is white light raw contrast measurements from the lab in air from this summer. Well, as we calibrate the instrument, the radial average in the middle shows that in our science region, we're reaching 10 to the minus 4 raw contrast. That's limited by air turbulence and some misalignment in our LEO stop. But even with that contrast and adding dark noise and photon noise, since we'll be taking a calibration PSF on Rigel during flight, we can subtract those speckles off, and we should still see very bright scattered light exozodi. So we plan to launch this winter, and that was, thank you.
All right. Hi, I'm Sam Grunblatt. My project actually has nothing to do with direct imaging, but so be it. In October 2013, both Andrew Howard and Francesco Pepe measured the mass of this planet, Kepler-78b, which is actually very difficult to do because the host star, Kepler-78, is actually very active. Despite this, they were still able to use parametric methods to determine the mass to within about 4 sigma. But combined with the original discovery paper of this planet, you could figure out the radius of the planet, and you can actually place it on this mass radius diagram. It's this black cloud down here. But in order to beat the uncertainties down, we want to be able to better understand the stellar activity. And so in order to do that, I used a Gaussian process regression with a quasi-periodic kernel function. And next slide, please. And so what that allowed me to do is, so first I took actually the original Kepler photometry and was able to fit it with this Gaussian process regression. And that's actually justified because a lot of the noise that you see in the Kepler photometry is the same as the noise that you're going to see due to the star in the radial velocity measurements, so such as like the stellar rotation period, stuff like that. And so I was able to use that Gaussian process fit, and then apply it to both RV data sets, both the high-res and the HARPS data sets. And by doing that, I was able to then, by fitting both the high-res and HARPS with an MCMC analysis, after I subtracted the planetary signal, I was able to fit both of them with their own Gaussian processes, and then with one single planet parameter. And by doing that, I was able to extract the planetary signal with about 25 to 30 centimeters per second precision, which is corresponds to detection of about 6 sigma. So it was a good improvement over the previous studies. Thank you.